we're going to evaluate the triple integral over q of x dv in the first octant where q is enclosed by the plane z equals 0. That's just the xy plane. Z equals y plus 5. And the cylinders, x squared plus y squared equals 4. And x squared plus y squared equals 9. So what might that look like? Well, I'm going to graph. I'll show you what I'm going to graph. And with a little experience, you'll learn to do this too. I think I can avoid graphing the full cylinders. I can graph what they look like in the xy plane as circles. But if you graph too much here, you're in danger of it getting a little bit messy. So I can graph y equals z equals y plus 5 pretty easily. And z equals 0 is just the xy plane, so it's kind of automatically there. So we're going to imagine this is the x-axis sticking out of the screen. Positive x-axis, positive y-axis, positive z-axis. So z equals y plus 5. In the yz plane, which is the plane of the screen, what is z equals y plus 5? What does that graph to be? A line, yeah. A line. And so it's like y is like taking on the role of what you usually call x, and z is taking on the role of what you usually call y. So what's the z-intercept then? If you plug in 0 for y, you get z equals 5, don't you? Okay, so let's count up 5. There's your z-intercept. And then what's the y-intercept going to be? Negative 5? So yeah, if you plug in 0, leave y alone, plug in 0 for z, solve, you get y equals negative 5. So let's go in the negative direction on the y-axis. And then we'll draw in that line, and that line generates the actual plane that we're talking about in space. So I don't know how far I need to draw it, so I'll just be on the safe side and draw it a little longer than I think it needs to be. Now, the perspective I'm using, it's going to be pretty tough to actually turn that into a plane, isn't it? To make it look, in other words, I'd want to turn it, I'd want to rotate it to the left or rotate it to the right. But you know what? I don't think I even need to do that. I just need to get the ceiling and the floor. And I think I'll be good to go here. So if you think about it, the floor of the object that I'm integrating over is just going to be the xy plane, isn't it? So this guy's the floor. At least part of it anyway. A subset of the xy plane is the floor. And this guy is going to be my ceiling. And then what are going to be my walls? What's going to form the walls? Well, if you think about it, what does x squared plus y squared equal 4 look like in the xy plane? X squared plus y squared equals 4. That cylinder breaks down to just a circle, right? A circle of radius 2. Okay. So a circle of radius 2. Oh, I'm going to try and freehand. Don't laugh too much. So that's x squared plus y squared equals 4. And then x squared plus y squared equals 9 is a circle of radius 3, right? Okay. So I'll try and freehand that as well. So the part of the floor I'm talking about, the subset of the xy plane that is the floor, has got to be in between x squared plus y squared equals 4 and x squared plus y squared equals 9, right? In other words, it's got to be in here. So that's the part of the floor we're talking about. But if you extend these circles, if you translate these circles parallel with the z-axis, you get cylinders, the typical tin can shaped cylinder, right? Generated by a circle for both of those. And so the walls would be in between those two cylinders, right? Would you agree with that statement? Because it says in the first octant where Q is enclosed by the plane z equals 0, well, that's going to be that part of z equals 0 is the floor. The donut is the floor. Z equals y plus 5 is your ceiling, and the cylinders not only help you come up with the floor, but also the walls as well. The other thing it does say is it's in the first octant, so that restricts it even further, doesn't it? Yeah. So how about right there? Would you buy that? Okay. Now notice I didn't draw much in 3D here because it was, at least from the perspective I used, it was kind of tough to draw, wasn't it? Now, if I wanted a better perspective, if you wanted to see what this would look like in space, I would maybe use this sort of perspective. So this would be the positive x-axis, positive z, and then maybe make this negative y. I'll put a negative on it. And then you might be able to get a better looking picture out of this, because if this is your generating line, I'm just sketching it here, you could translate it this way. And again, I'm just eyeballing it. Stop it somewhere over here. And then that plane, z equals y plus 5, then is looking like that. So if you really wanted to draw it in 3D, you could. But then, of course, this, it's kind of like a lean-to almost, is hanging out. The part we're interested in is actually, you'd actually have to extend this a little further, wouldn't you? Because the part we're interested in is the part that hangs out over, and that's why I didn't try to draw it. It's really tough to draw using that perspective. But it's the part that hangs out over the region we tried to indicate in blue right there, right? But that's a easier perspective to draw from, so I just wanted to mention that real quick. Anyway, enough fun, enough messing around. The triple integral well, okay, it's cylindrical coordinates, right? So automatically, we'll handle the x right here in a second. Automatically, what are the differentials going to look like? It's got to have an extra r in it. dz, dr, d theta. What does the x turn into? R cosine theta. Okay, z. Okay, so z, what does z run from? So if z is in the floor over here somewhere in the first octant, because the y-axis goes on, the positive y-axis is over here. So z might be, a point in the xy plane might be over here. So say it's this point right here, for the sake of argument. Then the floor would be actually in the xy plane, and you could draw a vertical line, okay, up to the ceiling like that. So use that. There's your lower limit of integration, height-wise. Think of the z value of this point in the xy plane. Your upper limit of integration, think of the z value of this point that's hitting the plane, and you get your inner limits of integration. So what are those values? 0 to, what's the equation of the plane? What's the equation of the plane? Well, normally it'd be y plus 5, right? But Ryan, what do we have to replace y with?
R sine theta.
That's almost how a pirate would say it. R sine theta. Plus. So that's the y, but then we also need the The plus 5 still, right? Okay. Everybody with me? All right. And then project down into the xy plane, and you get this region in blue right here. And draw in a spoke, draw in a representative spoke. Now, I'm going to draw this first part of the spoke with a dashed or dotted line because it's not part of what I want. The part of the spoke, it's too dark, I can't see it. So how about let's do it in orange. So the spoke that you draw, the part of the spoke that you draw would be right here. Can you see that? It's not coming up that clearly, but from radially out from here to here, right? That's the part of the spoke that we want. And the ends will give you the limits on R. So the one closer to the origin would be the lower limit on R. What would that be? 2. Yeah, that would be the radius of this inner circle, which would be 2. So from R equals 2 to 3. Everybody with me on that? Okay. And then theta's going to have to, since we're just in the first quadrant, so 0, 2, theta runs from 0 to pi halves, yeah.